on the Putra Blast as well. There's a lot of problems together with the solution, so you can download it. All right, so you can go through which maybe part of the problems will be on your test too. Okay, so there are hundreds of questions on for all of the topics that should be covered, which is from the chapter 6, all right, work and energy, up to the fluid mechanics. Okay, so you can use that, right, as the reference, okay, for you. I mean for your study notes. Okay, so that's probably is actually including all of the solutions together. All right. Okay. Any other? Do you have any question before we start with the chapter 14 today?
No.
Okay. If there's no question, then let's start. Okay. So we are on the new topic, which is the periodic motion. So as you know that the periodic motion, we just did the lab. Okay, we just did the lab 2 weeks ago. Okay, which we have the pendulum. All right, have the pendulum, and then we know that we can plot a wave. All right, so from the wave we can actually calculate the period. Okay, the period of the, okay, and the frequency, okay, and so on, right? So that's about the periodic motion. So today we're going further. All right, we're going to discuss the theory about that. Okay, so the pendulum experiment is about the simple harmonic motion. Okay, so we also going to learn about the oscillation and also the resonance. Okay, all right, so we observe that the motion of the dog, okay, so why it is faster than us, all right, does it has anything to do with the characteristic of their legs? Okay, so that depends actually. Okay, so you see that we are much slower, all right, so mean that the dog, okay, needs to be quicker. All right, it looks quicker because it has a shorter legs. All right, of course when it has shorter legs, so the period will be much shorter, so that's why we look it is much faster than us. Right. So there are many kind of motions such as pendulum. Okay, so we have many other things that the things that are going back and forth to the original position is we call that as the periodic motion or oscillation. Okay, so that's such examples. Okay, so what caused the periodic motion? Okay, so below over here we have example of the object attached to a spring. Okay, and then if we move, okay, we move the object towards a spring, okay, mean that the spring is compressed. Okay, of course the spring will, okay, will revert back to its original position. Okay, to its original position. because that's the behavior of the spring to restore, okay, to restore its position. Okay, so this force, so we have called that this is a restoring force which cause the oscillation of the system. Okay, so this is what is the periodic motion. Okay, so we looked at the force diagram. Okay, so we have the Fx, and as usual, we have the normal force and also the weight of the object. Okay, so Fx is moved towards the left. Okay, so when we put a force on that, okay, so when it is at the normal position, okay, then there is no force. Okay, there is no force. And then when we compress it, there is an acting force, okay, on the right. Okay, because now this the spring in the compressed condition, okay, the spring in the compressed condition, so it push the object, okay, towards the equilibrium position, to its normal position. Okay, so from here, so what do we have? Okay, is the when there is a periodic motion, so these are the important things that we need to note. Okay, which is the amplitude, period, frequency, and the angular frequency. Okay, so angular frequency often we have when there is an oscillation. Okay, so amplitude, of course, you know, so the maximum magnitude of the displacement, okay, from the equilibrium. Okay, so the period, okay, it's not a problem as well. So F is also equals to 1 over T. Okay, and the angular frequency is the omega. Okay, so it's actually 2 pi F. Okay, so when we have the simple harmonic motion, okay, this is happen when we have the restoring force. Okay, so we look at the spring experiment over here. So this is actually the restoring force, the Fx. Okay, it force, okay, it force to restore back to the original position. Okay, so that's the restoring force. Okay, and then this restoring force is directly proportional to the displacement from the equilibrium. Okay, so this restoring force is proportional, meaning that it is linear if you plot in the graph, okay, to the displacement that you applied. Okay, so it'll be in terms of negative slope. Okay, when you plot the graph of fx versus x. Okay, so this is where we obtain the Hooke's law over here. So the Hooke's law is equals to minus kx. Okay, it is minus kx. Okay, so that's the relationship between the restoring force and also the displacement, which is defined by the Hooke's law. Okay, in many systems, the restoring force is approximately proportional to the displacement if the displacement is sufficiently small. Okay, right? So meaning that if the amplitude is small enough, the oscillations are approximately simple harmonic. Okay, so you can see that sometimes when Hooke's law is not obeyed, right? So we look there that we have that restoring force versus displacement is not as linear as it should be. Okay, but in the some moment, all right, in some moment, we can see that it's still obeying. Okay, somewhere around here, if you can see from the graph, it is still obeying the Hooke's law. Okay, if due to the displacement is sufficiently small. Okay, but in the real case, okay, in the real case, usually this is what will happen. So we have the deviation of the restoring force from the displacement. Okay, so in order to find out what is the k value, so we just need to use the plot which is linear. Okay, in that we take the point from over here to somewhere over there. Okay, in that it is based on the small value of x. Okay, so when we look at the over here at this moment, all right, this is what we call that the simple harmonic motion, because it will nicely follow the period. Okay, so this is the simple harmonic motion. Okay, so that is followed. So that's the simple harmonic motion. Give me one. Okay. All right. So if we view that, okay, as a projection, okay, so we have an example here. So we have a ball over there, okay, and then we have a light beam. Okay, when the ball, so the ball mentioned as Q, okay, on the turntable move in the uniform circular motion, okay, its shadow P moves back and forth. Okay, so it will move, okay, somewhere from there and then goes to there and then goes back to there, and okay, it will, okay, goes back and forth, okay, from one location to another location. Okay, so you can see that, so that's the shadow of the moving ball. Okay, so that's if the ball make the direction, make the what we call clockwise direction. Okay, but if it is turned into the counterclockwise direction, so it will start from here, P, it goes to minus A and then back to O and go back to A and so on. Okay, so that's the motion of the ball. Okay, so we're going to plot this, all right, we're going to plot this, okay, on the graph, and then this is what we can see there. All right, so let's say this is the location P. Okay, so this is what we will see. Okay, so the motion of the ball following this circle, okay, is called the reference circle. Okay, and then as this point, okay, this point Q move around, okay, around this circle, okay, at a constant speed, okay, So the constant angular speed, so when we make the circular motion, okay, the vector OQ rotates, okay, with the same angular speed. Okay, so this vector, okay, from OQ, okay, will also rotate. So this is the vector, will also rotate with the same angular speed. Okay, so this vector, okay, is called as a phasor. Okay, it is called as a phasor. So you will learn more details about on how to solve the phasor during the electronic subject later. Okay, PHY3306. Okay, so that is a phasor. Okay, so from here, what do we have that? So this is the important equation that is related with each other. Okay, so we have, when we have this motion, so of course we will have the what we call the angular speed and also the angular frequency. So when there is an angular speed, there will be an angular frequency. Okay, so we define that omega as the angular frequency, okay, which is equals to this, okay, the square root of k over m. Okay, so it depends on the mass of the object. Okay, and k, where we obtain that from the Hooke's law. Okay, so that's the relationship for the omega. Okay, and from this omega we can also obtain the frequency. Okay, we can also obtain the frequency. Okay, so once we obtain the frequency, okay, so that's the relationship is 2 pi f. Okay, 2 pi f. From frequency also we can obtain the period. Okay, we can obtain the period, so which is 1 over f. Okay, so if you want to mention, okay, that period t in terms of mass and k, okay, so it is equals to 2 pi m over k. Right, so that's the relationship. Okay, all right, so we'll go further. So that's example is simple, so you can just go through by yourself. Okay, so we look at the characteristic of the simple harmonic motion. Okay, so when we have the bigger mass, okay, so we have the lower frequency of the oscillation. Okay, okay, for example, over here we have a tuning fork. Okay, so whenever we have the greater mass, so this bigger one, okay, it has the lower frequency of oscillation and the lower pitch of the sound that the tuning fork produce, okay, due to lower frequency. Okay, so we look back over here at this equation. So when we have bigger mass, of course we have smaller angular frequency. When we have smaller angular frequency, so that also contribute to the lower f. Okay, so when omega is low. Okay, so when the that's why when the small object is moving, right? So we have a very noisy, okay, very noisy oscillation. So that's what happened when we rotate, let's say, a small fan. Okay, a small fan compared to a big fan. You can hear that. So when there is a small fan, okay, compared to big fan, so that's the fan, your ceiling fan. Okay. So due to that, Okay, when this fan is small, right, then you will hear that the noise from the fan is much bigger than the bigger fan, right? So that's actually relates to the characteristic of this simple harmonic motion. Okay, so this is the equation, all right, for the displacement in the simple harmonic motion, where okay, we have this relationship. Okay, so the equation states that x equals to a cos omega t plus phi, right? So this is okay. Omega is the angular frequency, okay, and phi is the phase angle. Okay, so the phase meaning that if there is another thing okay, acting on the object, so let's say we have two graphs, okay, like that. Okay, so we can calculate the phi, okay, in that the phase, okay, meaning that from here, from this location up to that. So that is the phi. Okay, so this is the normal graph. Erase that. Okay, so this is half order period. Okay, so this is one period. Okay, or if you want to draw that from here, so that's also one period. Okay, meaning that from 0 to 0, or from A to A. Okay, so that's the period. Okay, and x is the at the maximum value is the amplitude. Okay, so when we increase the mass, okay, what will happen to the graph? Okay, so with the same amplitude, okay, k increases the period of the displacement versus time. Okay, so you can see that with the mass increase, of course, we learn from here that we have a lower frequency. Okay, what happens when we have the lower frequency? Meaning that the time taken will be longer when we have the lower frequency. As you mentioned that, as you remember that t equals to 1 over f. Okay, so when we have lower frequency, of course, time taken to be higher. Okay, so when the time is higher, so we see that okay, this is when we have a smaller mass from 1 compared to 3, okay, which has all right, which has um bigger period compared to 1. Okay, so you look at this is the period of 1. Okay, from here that is T1 compared to T3 over there. Okay, that's the T3. So from here up to there. Sorry, up to here. Okay, so that's your T3. Okay, so when we increase n, so that increase the period. Okay, so when we increase k with the same a and m, okay, we need the force that we apply, okay, the force that we apply. So if we move, let's say the pendulum, So this is the pendulum. Okay, or like the spring. Okay, like the spring. Okay, this one. When we apply a bigger force, let's say when we apply the force, so when we increase that force, okay, so mean that we increase the K, okay, with the same A and M. So M, okay, decreases the period. Okay, so we can see over here, the force constant K, okay, increases from curve 1, 2 to 3. Okay, so curve 1, okay, okay, this one have the smallest K, okay, smallest K, okay, and then this is for 1, and you look at the third one, we have higher K. Okay, so what is happening? So when is increases, we have a smaller period. Okay, when we have a smaller period, so meaning that we have a bigger frequency. Okay, so that's the relationship. But over here, we still remain our amplitude. Okay, we still remain our amplitude. Okay, let's say now we increase the amplitude. Okay, when we increase the amplitude, so again, back to the pendulum experiment. So over here to there, okay, compared to there. So this is when we have the at 1, location 1 to compare to 2. So we have a bigger amplitude over here, okay, compared to this one. Okay, when we have this, okay, when we have this, it does not change the period. Okay, it does not change the period. Okay, and also when does not change the period, of course the frequency won't change. Okay, only the amplitude change. Okay, so remember that. Okay, so okay, when we increase the phi, okay, when increase the phi, so this is phi, as I mentioned before. So we look over here, this is the original one. Okay, so for this one, for the blue one, compared to the gold one, so we have the phi is from there. Okay, and then for the pink one, so we have the phi is at the middle of that. So that's phi. So phi equals to pi over 4. This one, as you can see that, quarter of pi, and then another one is uh, pi over 2, half of pi. Okay, so remember that. So one oscillation, okay, so one oscillation completing one period. So we have 2 pi. Okay, so we have 2 pi from here to that. Okay, we have 2 pi, and half of that we have pi. Okay, so half of this, okay, half of that, that's why we have pi over 2. Half of this one, pi over 2. And half of that, of course, we have pi over 4. Right? So when we increase the pi, so we have still we have similar A, okay, okay, and K only shift. Okay, so we have A, M, and K are all similar, except that we have the shift in terms of the graph. Okay, so that's the effect, okay, when we increase the phi. Okay, so when we have this graph of the displacement and velocity, all right, so we look over here, the graph, okay, x is shifted by 1/4 cycle from the xt graph. Okay, when we see that it is shifted. Okay, so when this is shifted, okay, so what happens here is actually the phase, okay, it is out of phase. Okay, so meaning that the phase is changed. And then if we replace that, okay, with this, okay, with this one, the amplitude is omega A. Okay, so this is equals to also, okay, omega A, right? Also omega A. And then we note that the equation that is given here, okay, well, it is sine theta, all right? Sine over here because it starts, okay, it starts from, okay, an amplitude. Okay, so that's why we define it as sine. Okay, but when it starts at somewhere around 0, okay, we use the cos. Okay, so that's the graph. Okay, then we have the graph shifted, okay, by 1/4 cycle, okay, from this VTX graph and half cycle from the XT graph. Okay, so this is what we will have. Okay, so this is, for this we have the speed graph, okay, Vx. Okay. Compared to this one, we have the acceleration graph. So what we have here is, okay, the difference is this one. Okay, the equation of that. So we have minus omega squared, okay, amplitude, okay, and then others are still similar. So compared to this one, okay. So that's the relationship of the graph of displacement, okay, and velocity. Okay, so this is for the displacement, this is for the velocity, this one is the acceleration. Okay, so that's the three different graphs for the simple harmonic motion. And then we also can calculate the energy. Okay, we can also calculate the energy. So where we have the energy as follows. Okay, so here the object is not moving, so the kinetic energy is okay at this location. Okay, and then it moves. Okay, it moves toward a location. Okay, for example, here is minus half a. Okay, you see that over here the total energy is conserved. Okay, so E is the total energy, it is conserved, except that we have change of K and also U. Right? So here object is not moving, so K is 0, so the potential energy is the highest. Okay, when we move it, okay, to that location, so K is moved, is increasing, okay, and u keep decreasing until at the maximum value where it moves at the higher speed. Okay, meaning that over here, okay, you can look at it at the higher speed, so Vmax, at the Vmax, and then this is only square root of 3/4 Vmax. Okay, and then goes back and then keep decreasing, and then the K decrease until we have back. So at this moment where we have U at the highest, where the object is not moving. Okay, so the equation for E for the kinetic energy K is equal to half mv squared, okay, plus, so U, the potential energy is defined as half kx squared. Okay, and combined together with this equation is equals to half ka squared. Okay, all right, so that is the relationship. So we look at the example over here.
In example 14.4, we're going to return to the glider that we studied in example 14.2. In the first part of 14.2, we tied a scale to a spring and stretched the spring out a certain distance and measured the force on the scale. This told us the force of the spring and allowed us to calibrate the spring and determine the spring constant. The second part of the problem, we removed the scale and attached a 0.5 kilogram glider. We then pulled the glider out to a distance of 0.02 meters and released it, and it oscillated back and forth on this frictionless surface. We'd like to calculate the maximum and minimum velocities and accelerations of this glider. We'd also like to calculate the velocity and acceleration when the glider is halfway between its maximum displacement here and x equals 0, so right there. We'd also like to find the total energy, the potential energy, and the kinetic energy of this position. So let's begin with the equations that we'll need to execute a solution to this problem. The amplitude of the motion is 0.02 meters. We can use equation 14.22 to determine the velocity at any position by this equation. And the acceleration of the glider, of course, must be equal to the force acting on it, which is minus kx, the force of the spring, divided by the mass. And finally, we can write down the total mechanical energy of the glider as equal to the kinetic energy at any point in its motion plus the elastic potential energy of the spring. This sum must always equal to 1/2 ka squared raised to the amplitude, because when the glider is at this position, it's momentarily at rest, and all of its energy, all of its mechanical energy, has to be potential energy of the spring. So for part A, we'll use this equation, and we'll notice that since we're subtracting an x squared, that when x is equal to 0, we get the biggest value of this. And so the maximum velocity occurs when the glider gets back to the equilibrium position, and we can put in the values, and we get 0.4 meters per second. The minimum velocity occurs, of course, when x is equal to 0.02 meters, as seen by this equation. The maximum acceleration occurs when the spring is acting the strongest on the glider, applying the most force, and of course that will occur when the glider is at the maximum elongation, so that when x is equal to a. Putting in the numbers, we get 0.8 meters per second squared. So now we want to take the point halfway between a and 0. This is going to be a over 2, which is 0.01 meters. We can find the velocity there, plugging in the numbers, putting in x is 0.01, we get minus 0.35 meters per second. It needs to be negative, because the glider, after it reaches this point, is obviously headed to the left. The positive x direction is to the right. The acceleration at that point, of course, is very simple. Spring constant times the elongation divided by the mass. It's also negative. The spring's accelerating to the left. And finally, at this position, we can calculate the total mechanical energy of the system, which of course has to be 1/2 kA squared raised to the amplitude. That's 0.4 joules. The potential energy, putting in the numbers, is 0.01 joules, and the kinetic energy is 0.03 joules, where we put in the velocity that we calculated up here. And finally, we note that 0.03 plus 0.01 is equal to 0.04, as it should be, and that at this position, most...
All right, so over here, we look back. Okay, so we have what we need to find is the maximum and minimum value obtained by the oscillating glider. All right, so first we want to know what is the velocity. Okay, so we need to find out which equation that relates with the velocity. Okay, so as we know that, so this is our equation for the velocity relationship. Okay, so we have this. So Vx equals to plus minus. Okay, so which is the force? Okay, half. Okay, k over m. All right. Okay, so square root of a squared. So which is the amplitude minus x squared. Okay, so that's the relationship. Okay. So actually this is this one is actually can be actually taken from the when do the v squared. Okay, v squared. Okay, so this is omega, right? So this is omega squared a squared minus x squared. Okay, so that's the relationship. Okay, so from here we can also know what is our a. Okay, so by differentiate it 2 times, all right, so we have a. Okay, so when we differentiate that, we have minus k over m x. Okay, so these are the equations that is related. So directly, so we can use v. Okay, so what happened when we have the maximum v? Okay, so maximum v is obtained when x is 0. Okay, when x is 0. All right, so when x is 0, so when we plug in over here, so we just need to know what is our amplitude. Okay, so the amplitude will be, okay, over here is 0.02. Okay, 0.02 over here, and then our k, what is k? Okay, so it is given, so a is 0.02. Our k is 200 Newton meter. Okay, because over here, so we have our mass. Okay, we have our mass. Okay, we have our mass is 0.5. Okay, so k is the actually the relationship of k. F equals to kx. Okay, F equals to kx. Okay, so mean that the k equals to f over x, right? F over x. So that's we obtain. Okay, so the mass as right? The mass as 200, okay, Newton per meter, right? And then we have B. We have B. So B is A, right? So K is still 200 Newton per meter, all right? And then we have M 0.5 and A, the amplitude, okay, from here, it is 0.02. So it is easier, right? Once we obtain all of that. Okay, so once we have that, okay, once we have that, then we have C. C is to find out what is the, okay, so find the velocity and the acceleration when the glider is halfway. Okay, so when the glider is halfway, all right, so when the glider is halfway, so we obtain that, okay, we have the A amplitude minus halfway x. Okay, x is the halfway from here, so we see that, okay, it's moved, okay, halfway from here, so it is only 0.1. Okay, it is only 0.1. So where the total should be 0.02. Okay, when it is moved forwards. Okay, so halfway of that is 0.01. Okay, so once we have that, so we can calculate our Vx and also similarly our Ax. Okay, and the last one, the total energy. So we just use this equation. Okay, so we know that our A, all right, we know that our A, so we can just, okay, and all others are given. Right, so that's about example 14.4. Okay, so let's have a break for 10 minutes. Okay, let's have a break for 10 minutes and then we will continue after this. If you have any question, you can let me know. So we're gonna break. So we will start again around 10 to 9:15. Okay. Okay, right. Come back. Okay, by the way, so we'll continue as I mentioned earlier. So how about playing a quiz right now? Okay, so the topic will be the previous one. Okay, so you have your own pace. Okay, so it will be about the fluid mechanics. So we have 13 questions. Okay, so you see that. So you can join. So just look over there. Okay, I can see East is there. KJI is there. Right, also Balkis. Okay, Elia. Right, Munira. Who is Serendipity? Okay, so there's only 10 of you. Okay, I'm going to wait for another 1 minute. So after that, we will start. So, right, we have 1, 3, 13 students only right now. So 7 are missing. Okay, I'm going to count from 10. So we're going to 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You can start now. So Ace is leading. Let's see if anybody can compete him. Okay, I'm gonna wait until 9:40. Okay, and I will stop the quiz. Okay, you have 1 more minute to complete the quiz. So for the top 5, right? For the top 5, as usual, you get the extra mark. Okay. Okay. Majority of you have finished, alright? So that's the top 3 leaderboard for today. So he's got the first place, Faris got second, and third is Mashita. Okay, it's different name this time. Okay, so you're good. Okay, so if you look at the questions, all right, so just go through. So many of you got the correct one for question number 1. Okay, question number 2, right? So not so many. So let's see. Question number 10. Okay, question number 10. So you got many of you didn't do it correctly. Okay, anyway, I'm going to, if you want to have it, I'm going to give you as the assignment letter, so you can do it at your own pace if you want. So, all right. So congrats for those who got the top 5 for today. Okay, so let's continue back to the lecture for a little bit more. So after that, we stop. All right, so before this, we already calculated the energy diagrams. Okay, so we have, okay, so this is the energy diagrams that we have. Okay, so we look there, so we have the potential energy, okay, at the highest, at the maximum value, okay. So when we are at the highest position, let's say the pendulum, so it at the highest position, so we have the maximum potential energy, and then at the lowest point, so we have the maximum kinetic energy, okay, and then half of that we have similar K and U, okay, similar K and U at half of the motion. Okay, so all right, so this is the graph for the K. Okay, so K and U. So K will be inverted compared to U. So K is maximum over here, and then U is minimum over there. Okay, so you can look that. Okay, so that's the relationship between K and U. And then for, okay, so we have the pendulum and also we have the spring, okay, in the vertical motion. Okay, so the relationship is that we have the force over there, F equals to K delta L. So delta L is the displacement that we made. Okay, once we put the load on the string, so we have, when we put the load, and then the spring will go back and forth. Okay, go up and down, okay, couple of times. Okay, and then we see that the displacement of that, so it will still follow the simple harmonic motion. Okay, so we go back to that its own position and then goes back again downward and go back again upward. Okay, so that's based on the, but actually there will be a damping moment over here because due to what we have, that due to the gravity. Okay, due to the gravity. But if you do this experiment without the gravity, of course, it will always going back and forth multiple times. Okay, and then we also have another way we can do this experiment by inverting the spring. Okay, by inverting the spring. So we also have the similar thing to calculate. I mean, the similar way we can calculate it. So where, so the x, okay, the x is the length, okay, the displacement. So this is delta L is also similar to x, and mg is the force. Okay, so it is actually similar equation. Okay, so you still have the relationship of f equals to kx. Okay, and you also have the angular simple harmonic motion. Okay, so let's say you have the balance wheel, okay, put on the spring. Okay, so over here what you can see that we have this spring, okay, where we have the coil over here. So we have the top. Okay, when we have something moving in the circular motion, we will have the top. Okay, and then we have the spring below that. Okay, we have the spring below that. So how can I show it to you? So the spring is like that. Okay, so it's like a coil. Okay, so this spring coil, and then we have the balance wheel on top of that. Okay. All right, so the torque over here can be calculated using this equation. Okay, so where K is the torsion constant of the spring. Okay, and then over here we will have the angular as HM. Okay, angular simple harmonic motion. Okay, so that's the how we define the angular simple harmonic motion, where we have a moving object on top of the spring. Okay, meaning that the spring, okay, the spring will go up and down. Okay, will go up and down. At the same time, we have the circular motion around that. So we have the angular simple harmonic motion. Okay. All right. Okay, we look at example. So for example, we have also we can calculate the potential energy of a two atom system. Right, if we have two atoms over here, we look that, okay, so it will follow, okay, if it is in the equilibrium, okay, if it is in the equilibrium, it will follow the parabolic curve. Okay, it will follow the parabolic curve. Okay, so it's like that. Okay. So it has the potential energy at the highest. Okay, when we have a two atom. Okay, for example, it's like this one. Okay, for example, we have this one. So we have two atoms. For example, this is in, let's say this is just experiment in the physics. So just give you example over here. So we have two atoms, and we have the distance between these two atom system. So this is actually the potential energy of the two atom system. Okay. So we have the equilibrium point. So this is at two equilibrium point where we have, okay, this atom is together. Okay, when between together, I mean it is at the certain position, right? At a certain position. So once we have this, right? Once we have this, okay. So when it moves further, let's say at another distance, okay, over there. So for example, this is the initial motion, and this initial condition over here at R0, and then we have this atom, okay, moves further, let's say at that location, okay. So the potential energy between the two atoms, okay, is defined by this curve, okay. So it is defined by this curve. So mean that the potential energy at this location is at the lowest, okay, at the lowest, and then it will increase, okay, once it will be pulled apart, okay, it will pull apart at a higher distance, and then it will become zero. It will become zero because there is no more potential energy between the two atoms. Okay, so that's just the example of that. Okay, but this is the problem actually is much complicated if you want to define it, right? So I'm just giving you an example over here. Okay, so I'll speak this one. Okay, so we also have a simple pendulum. Okay, we also have a simple pendulum, so which I give you example before, all right? So we have the ideal pendulum, okay? So this consists of point mass, okay? Over here, point mass suspended by the massless unstretchable string, okay? So if the pendulum swings with a small amplitude theta, okay, with the vertical, its motion is simple harmonic. Okay, so as you can see that the simple pendulum follows the simple harmonic motion. So this is what you already know. Okay, and then you look at the force diagram over here. Okay, this is important. So you have mass, and then you have the tension. Okay, the tension as the force acting on the string. Okay, and then you have the weight. Okay, and you have the weight mg, and then this is the component of that. Okay, mg cos theta and then mg sin theta. Okay, so that's basically the force acting, okay, on the pendulum. Okay, so a physical pendulum. Okay, so over here is the simple pendulum, for which is we mentioned that is ideal pendulum. Okay, when we have the physical pendulum, okay, when we have the physical pendulum, so physical pendulum is any real pendulum that uses an extended object instead of a point mass bob. Okay. For small amplitude, its motion is still simple harmonic. But for big amplitude, okay, so if you increase further, okay, like that, it won't be a simple harmonic motion anymore. Okay, but for small one, it will still follow simple harmonic motion. Okay, so let's say from there to there. As you see that this graph, okay, this is related to this graph what I mentioned before. Okay, this one. Okay, so this is won't be this is what will happen, okay, when you have a real pendulum, mean that the mass is not a ball. Let's say this one is like pendulum. Let's say you are hanging over here, like that. So it's like pendulum, right? So when you swing from back and forth, okay. So your motion at this location, somewhere around here, is simple harmonic. But when you are at the very high amplitude from here, okay, because if we show you the graph like that, okay, something like that, okay. All right, so this is based on the time. Okay, other factors, other dampening factors will follow. All right. Okay, so that is the physical pendulum. Okay, so you can just look at the example by yourself. Okay, so another example is the T-Rex. Okay, the dinosaur T-Rex. Okay, so this one can actually show us relate that with the physical pendulum. Okay, if you want to know further about this, so you can just find out some information about this, right? And then it's actually uh, the motion, okay? So the motion, okay, is following the simple harmonic. So because the T-Rex will use its leg, okay, actually from there it move, okay, and it, this will swing, okay, this one will swing, the legs will swing, okay, go back and forth, okay, like that. Okay, then it follows the simple harmonic motion for the small straight line over here, and then but for the big straight line, it won't follow the simple harmonic motion. So that's why it is rated with the physical pendulum. Okay, so that's such an example on the physical pendulum. Okay, this is what mentioned. We have the damped oscillation. Okay, so this is what will happen in the real world. Okay, okay, because we have let's say the friction due to air. Okay, so that decrease the amplitude. Okay, so this is called damping. Okay, and the motion is called as a damped oscillation. Okay, so for example, if we have a very strong damping force, okay, so like B, this pink one, so if we have the stronger damping force, so we relate with this, let's say with this relationship. Okay, so when we see that we have the larger B, the amplitude, okay, will decrease more rapidly, and then the period increases. Okay, the period is increases. So this is what happening. Okay, so the period of this motion, okay, as you can see, it will be much larger compared to this one. It starts from there to here. Okay, that's for 1T, and then for this one, actually it starts from here. Okay, from there. So the period is much shorter, as you can see that. Okay, so it is about the damped oscillation. And we have the force oscillation and resonance. Okay, so this is the equation for force oscillation and resonance. Okay, so okay, so like this one, okay. So if there is an oscillator, okay, it's actually later you stop moving, okay. But if we maintain a constant amplitude oscillation by applying the force that varies with the time in the periodic way, so we call this additional force as the driving force. Okay, so this is the equation that we can use to solve that. Okay, so we have the damping constant over here. Okay, this is the angular frequency that is related. Okay, and then this is the driving force. Okay, so when we actually, okay, so like this one, like a pendulum, I give you another example again. We want to make sure it is in the motion, right? But actually the real one, in the real world, it will stop moving. It will stop moving after some time, right? It will stop moving. But let's say we want to make it stay, okay, follow the simple harmonic motion. Okay, so we apply a force, okay, F. So this is what we need to calculate. So F max, okay, the maximum value of that force. So we apply that. So we move, so we apply that force, okay, we keep applying that force, so it will keep you the simple harmonic motion, okay, like that. Okay, so this is the equation to calculate that. Okay. Okay, for example, in the real world, we have this lady beetle flies in mean of force oscillation. Okay, so it's not like the wings of bird. Okay, the insect wings are extension of this actually skeleton, right? So we apply this, all right? So it have a force oscillation. So you see that when wing of the insect, okay, it will follow a simple harmonic, okay, motion, and we have the oscillation, okay, because it goes back and forth, right? Okay, but in order to make it stay, okay, stay like that, there will be a force oscillation by the body of the insect, okay, by the body, so it will force it. So that's why it will follow this equation. It will follow this equation. All right, it will follow this equation. All right. So that's about the force oscillation. Okay, so that's it for this topic. All right. Okay, so as usual, so let's take attendance for today. Okay, could you please turn on your camera? Okay, I'm gonna count from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, give me one more shot. Okay, thank you everyone. Okay, have a nice day and enjoy the rest of the day. Okay, assalamualaikum and bye-bye. Okay.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.